Yeah, good morning. Welcome. An American, an English, and a German are captured and sentenced to death. And they have one wish. So the American says, I want a Coke. And the German says, I want to give a speech. And the English says, I want to be killed before the German gives his speech. Now you're out of luck. And let me start. About 1.5 years ago, the United Nations AI Advisory Group requested the ITU in Geneva to work on deepfakes. And so the ITU turned to its technical experts and said, work on deepfakes. And I want to take you on this journey because we started with, is there something we can do about deepfakes? So I will talk about deepfake creation, deepfake detection, then the threats posed by deepfakes a bit, and then I will take a turn to authentication of multimedia, and then how to break it potentially, and what to do against breaking it. So it starts with deepfake creation. Image manipulation is not a new subject. If you look at this picture, I tried to find who that missing person is, and I couldn't. So that's actually successful image manipulation. And that is an addition to an image on the right-hand side. So the left is the original, and the right is manipulated. And so it has been around for quite a while and has been used for misinformation. There are several categories of deepfakes. I will concentrate on those that involve humans because they are the ones that make can produce most damage. So we have face swaps where you leave everything else but take the inner part of the face and replace it with what you want it to be replaced. Then you have a face reenactment where you take a face, you typically map a 3D model onto it, and then you can manipulate this 3D model, and the person is then doing and saying what you want it to do and say. Or you have a full deepfake on the right-hand side that appeared in the Wall Street Journal. And there are quite a few tools to create deepfakes. As you know, I have sampled a few, like Deepface Lab or Jiggy and then there's a tool where you have a bear that comes in. But from a scientific point of view, if you do an AI-based image synthesis, there are essentially 3 very relevant methods. One is an autoencoder, where you have an image-to-image transform. So you would train a video sequence with one person and train it with another person, and then you essentially swap the decoder between those two, and you get one person mimicking the other person. You can make this even better by running a diffusion model, where you create a noisy sequence on the way forward, and then on the way back, you use the autoencoder to basically come to the result you want this to be, and statistically speaking, that result is even better. And then you can also use GANs to create deepfakes where you train, compare, and basically see if what you trained and compared is detectable as being a fake or not. And you would train the generator and the detector, and you iterate between the two, and this way you can create a full image synthesis. Here's an example of some work. So we have basically replaced the face of the lady in the right-hand side. And I keep asking my folks, can we just make more dramatic replacements? But they say it's actually important that you are tricky, so that it's like you can have her say whatever you want, but there's some similarity, because there are limits also to what you can actually fake. a deepfake via diffusion. So you basically start with the original image, you use that autoencoder decoder, and then you have the diffusion upsampler, and you come up with this upsampled deepfake. And here's a result again, but you have a different person put into the diffusion image, and this is where you can actually come up with lots of manipulation. One thing that I wanted to mention, we just managed to publish, is at Europe's 25, which I believe is like this week or next week happening, is to create Gaussian splats using deepfakes. So you would basically train from a model's picture. You would basically have some positional encoding to align it, and then you have a multi-resolution approach where each of those adaptive transformer blocks creates some Gaussian splats. You then upsample, and then you create again a Gaussian splat, and so on and so on. And you can then create a person's 3D appearance based on deepfake, and you can manipulate it the way you want it. Here's an example of some work of somebody else. So you can see where the limitations are, that the head is cut off and the face shows some artifacts. Here's another result. And this is our result. You also see it's not perfect, but more of the face is preserved, and we are actually working towards making it better. So in a way, we are contributing to deepfakes ourselves. And it's also very useful in a number of applications. Now it doesn't want to move on. So last but not least, you can then produce an entire movie using deepfake. And that also tells you something for the movie industry, how that will be changing using these methods. Talking about so then we can create all these deepfakes. So how do we detect them? One method that's pretty often used is looking at the noise patterns, and you can actually see different structures of these noise patterns depending on the GAN, for example. The deepfake was created because it has certain artifacts that it's being created. So the real image noise pattern would be on the left-hand side, and then the GAN would be producing all these different patterns. But, well, bad news, what happens when you then apply a diffusion model, you can actually bring the deepfake to look like a real image. So you can basically mask your deepfake to not be detectable with this method. Another one is a CNN-based deepfake detector. Same thing here. If you train it on a certain deepfake, it very nicely detects these kinds of deepfakes. If you bring in another deepfake, you won't be able to detect it. And so on. The story goes on. We did ourselves use our LRP method, layer relevance propagation, where you have an input image, you have a neural network and cancer as a result, and we wanted to explain that. So for that we developed this LRP method where you would, in the forward path, take the output and compute by a Taylor series, a backwards function that would take the nonlinearities of the neurons and create an inverse mapping, and that would produce a heat map. So for instance, here you would recognize a castle, and the heat map would tell you with red, this is why I have recognized the castle. And you would basically can use this to analyze your neural network, whether it's doing what it's supposed to be doing. And for instance, we used it to analyze some challenges in AI classification. One of the big classification successes was to recognize horses. And then our method basically pointed to the lower right, and we found that almost all pictures in that challenge of horses had a copyright statement. And so basically the classifier learned the copyright statement. So this is how you can use that method. Or here, context, so all the ships had water with them, so we would actually recognize the water instead of the ships. Now you can do the same for deepfakes, and what you will see is that the LRP will give you a good result to detect deepfakes versus original images. If you want, for example, train it to eyes or other things. So we have also tested that, and it works quite nicely. And then we found also a method to make it fail. The last nail to the coffin is pulse and blood flow analysis. That's a method that's been used to detect deepfakes. So when I point a camera to your head, I can measure your pulse. And you may guess what happened this year in March. A first deepfake appeared that had a pulse. So long story short, and it was fun to put these slides together, we will lose the race of deepfakes. We will, in a few years, not be able, whether or not certain things are faked or not. I 100% believe that's going to happen. And we may already not know that certain things are faked at this point already. And there are threats posed by this. So you can create media clips, you can spread misinformation, you can manipulate public opinions, elections, all of that we have seen. It spreads fast via social media. There was a clip of Vitaly Klitschko that would trick the Berlin mayor in 2022. You can do identity fraud with it. All these methods where you identify over a video phone, all of that can be tricked with deepfakes. I just learned that there are job interviews from both sides that are faked. So the applicants are in AI to find out what the job is about and what the company is offering, and even the interviewer can be a deep fake to get your personal information. As long as AI does it, you can run this on scale. And of course, financial transactions. For instance, CFO tricks employer into transferring 25 million, or there's a fraud. It's everywhere because we are making decisions over our video phones, our chat methods. Imagine a company call where the CEO announces 50% of the jobs are being cut. Even if it's fake news, the stock value of that company will have a hit. And if you bet on that, you can make a lot of money. There are announcements, there are important things. There can be even other bad things happening, even when kids have education. And So then we thought, if we can't prevent deep fakes from being made, if we can't detect them, what else can we do? So the other route is to identify original camera content media. So you would enable a technical way of determining that this content has been captured at this camera the way I see it. And the way of doing this is not through watermarks or other methods, because they have their problems and challenges, so we can discuss them, but through digital signatures. You know them from your email. It's a very simple approach. You just create, on top of whatever digital content you have, some additional information that is being transported together with your content. And that additional information contains enough information to tell whether or not the original content is the same as captured. Let me go into some more details. So once that was identified, we started the standardization work to integrate the digital signatures into multimedia. So in ITU-T, Study Group 21, and ISO-IEC ST29, and these organizations develop the most deployed standards for video and audio, as you know. And we basically are augmenting the existing video and audio coding standards with this authentication mechanisms. And we allow basically a video, an audio, segment-wise, connected, synchronized to be authenticated. How does that work? So you basically, let's say you have your encoding device, for instance, can be this, and the manufacturer of that device and hardware has the following function programmed. They compute a hash over the bytes in the compressed domain. For video, it's really important to do this in the compressed domain. And that hash, for instance, 16 bytes, is encrypted using the private key of that manufacturer. So and then you transmit, and at the receiver, you decrypt the hash value, and you reapply the hashing mechanism, and you compare the two, and you know it looked exactly the same. What does that tell you? It only tells you that if nothing is broken, that at the moment of recording, this video looked the same as it is looking now. In addition to just taking the bytes of the video content, you can also include other information about the original of the video. For instance, the time it was taken, the location, and you can hardware side draw those things not to be manipulated. You can draw other information, meta information, for instance, the IMU data of the camera when the thing was recorded, and you would apply the same to also the audio signal. If you have multiple stations of encoding, so you have the camera capturing, then you have a transcoding, you would then have a different entity, a different company most likely, that would then validate the integrity of the content and do their transcoding and basically add their own hash value encrypted with their own encryption method to the list of hash values. So you can cascade these things, but at the end, the only thing you get, technically speaking, is an information over a trusted authority, one after another, doing certain things. And this way, you kind of have a chain of custody for the content that you're having there. For the private public key, you need a trusted authority to register the public key to be accessible. You would, one more feature of this, since you are adding this information, if it's removed, the authentication is gone. So it's a completely a positive acknowledgement kind of effect. If the acknowledgement is not there, there's nothing being acknowledged. So for video coding, we have added this to H.264, 5, and H.266. You can have lots of flexibility to include this into the data stream. You can have scalable video streams to be authenticated this way, and can also do video editing to a certain degree with this method. Oopsie, this one. Anyway, you can use, for instance, you can use this for a video conference. There's some picture missing that was here before. You can use it for some video conferences, for example, live. You can combine the authentication message together with the request for the speaker to identify herself, himself, through biometric usages. So you basically have to put your finger every 5 minutes onto a pad to say you're still a person in front of everybody else speaking. You can use this in live broadcasts and for other applications. There has been an organization called C2PA that have been doing a lot of these things about content provenance and authenticity, and we were lucky to be able to build on top of what they've been doing, because they've defined all those how to say, non-technical terms that come with authenticity with regards to provenance, etc. And so what we've basically been creating is a way of transporting this C2PA manifest in the multimedia stream so that it can be authenticated. Now I'm getting a bit into the geeky part of this, but some of you guys know this stuff, so I didn't want to take it out. So you basically can transmit this using supplemental enhancement information, which is a special part of a bit stream, which allows you to augment, send metadata, etc., and you can basically have the controls. You have the SCI message that tells you for which part of the video you apply the hash, because you need to basically describe that. I'm gonna skip this one. So then you can basically then create these bit streams with chunks, and you basically have substreams with identification. You have a file format, and you put that all together, and you can extract, verify, etc., etc. This is all being specified. And we did the same for audio coding. So those 3 most used audio codecs here contain the same, and there's also provisions to avoid peak bitrate overshoots because of this aspect, because they have very low bitrate sometimes. And then we also found a way to synchronize audio and video, synchronize the authenticity, because sometimes you could have an authentic video, authentic audio, but they both do not belong together, and suddenly you have something else fake. And the way this could look like in your social media would be like this. So the green dot tells you this is authentic. And we created Independence Day a la Berlin. Now it's not authentic. Authentic, not authentic. And it's a new revenue stream for the city of Berlin that we have suggested here. So what we hope is that this method that I talked about is being also incorporated into your favorite way of consuming media. So, for instance, in the social media side. And we also work on authentication at the systems layer. There, some of the aspects that we need to specify for audio and video have already been specified, so it's much simpler to put it in there. So, and that work is ongoing in MPEG. And so, to discuss this point, so digital signatures provide information that the media had the hash content at the device of the private key owner. That's all we get. But I believe this is a big step forward. The authentication approach works like a positive acknowledgement. So when removed, the media lacks the authentication. And when the media gets lossy, re-encoded, you can basically create a chain of authenticated, trusted information. And that's the chain of custody. So now, how to break it? So one obvious way is if you took a camera that's authenticated and you filmed fake video from a screen. Currently, you can actually detect that because the screens do not have such high resolution, but we are assuming that there will be very high resolution for a screen, and that this part you can't detect. So then before I go on, I'm going to collect ideas. So anybody have an idea how we can detect? Please, yes.
Can't we use like a checksum using SHA-2056 for every single frame of a video or an image? Like when you distribute an image,
yeah,
as a metadata for the image, not a PNG or some other format, you include the checksum. For a video, you do it for every single frame.
This is basically what the authentication is doing. But the question is, if I now take a fake video, put it on the screen, and I film it with my camera, and starting with my camera, everything is authenticated, how do I prove that this is natural camera content?
I think fundamentally it's like managing a video fingerprint, right? It's like I mean the same content can be transcoded, I mean scale up, scale down, but still the same thing. So it's about a very robust like a video fingerprint which is resistant to transcoding as well as other manipulation, right? Because eventually, say when you create the content, you somehow have a fingerprint, and then this fingerprint itself is not corruptible. Then later on, I mean, you can authenticate it just without the third party, right? It's within the content. Just compare the fingerprints.
Well, again, assume that the whole chain from the camera to your display is working. It's not broken. The encryption method, the hash method will certainly not be broken. The encryption method could be broken, but let's assume it's not. I still film from a screen something that is fake. What would be?
How about a variable frame rate of the camera? Randomly around whatever it is, but randomly, then you might catch the switch of the frame on the display.
We did not talk about this before, right?
No.
Yeah, so for instance, you could have a random shutter. In order to currently film off a display, you would need to synchronize the way the pictures are being displayed with your shutter of the camera. And I think most of the smartphones have a rolling shutter, and then you could basically disallow synchronization of shutters between displays and the cameras when authentication is being used, or you could go ahead and have your camera take each of these images at random time instances with a random shutter. But I have two more ideas. I wonder if you...
We could use depth information if we can add another channel to the video and encode that information as well. Perhaps that could tell us
We didn't talk about that either, right? And it's interesting that your ideas come in the same order as my slides. Yes, so you can, most of these things have 2 cameras. And you don't even have to do this all the time, but you can at some point go ahead and just use the other camera to estimate the depth of the scene. And with the display, it's obviously all the same. And this way you could do the same. And you can actually also do that using microphones, right? So, I mean, I'm assuming, for instance, there's a press conference and somebody wants to create a fake version of that press conference. Then it's also difficult to have an elaborate device setup. But if you think of a crime scene that's being faked, there you may be able to set up more loudspeakers and etc. So, yeah, estimating the depth is another way of preventing filming off a display. And there's a third idea over there.
Infrared flashing from time to time with the detection whether we have the real content or not.
Yeah, that's also a method I didn't think of. Perfect. So you basically use other sensor data like LiDAR, infrared, etc.
No, even the same sensor, but switched to night mode, for example, because we know that we can detect infrared with the current sensors as well.
Exactly. Okay. So then the third idea that we came up with for this keynote. Because this filming of a screen is the most broader point when it comes to this authentication. And I just thought an academic exercise would be good to counterbalance that. So the third idea we came up is if you have global motion in your scene, then if you imagine you're filming off a display and you are storing the IMU data of your camera, then you would basically have to have an entire display be moved together with the camera, you know? And so you could also store the IMU data of the camera. So 3 ideas plus the extra sensors, plus if you store as much information as you can about location, time, IMU, metadata, you can narrow down everything very tightly. And I believe we have a chance with these approaches to basically, for the content that matters, that needs to be authentic, to also have a way of transmitting to the receiver that it will be authentic. So to summarize, deepfakes are becoming a real problem and increasingly important, and AI will make them indistinguishable from natural content. AI detectors, or any detector for deepfakes, will fail. That's my assumption here. If you go the other route, you authenticate natural video and audio content, you need to enable the transport of the digital signatures or whatever mechanism you're using to do this authentication. And the way we currently do this, we basically have this C2PA manifest, which is time, location, metadata, etc., which basically creates this, has this provenance information. And this enables, video conferences, random access, and live broadcasting, streaming multimedia, multi-layer scalable coding, splicing, ad insertion, flexibility, etc. So the video part of this has just been approved in the ITU, I believe, and also is going through final ballots in the ISO. And the audio part is a little bit later, but it will be next year, beginning next year. Lots of people to acknowledge. I couldn't mention them all. It's a big list of people who worked on this to enable that. With that, I thank you very much. A few more last remarks. Last time I was in Klagenfurt was 2002 at a meeting of ISO IC ITU That was here. Who of you was there as well? You were there? Matthias? Okay. That was basically the last real technical meeting for H.264. And it was at the university, at a lecture hall, which had one of these ramps. And I remember one fellow, I won't name him, yelling at me across the hall about whether or not we can have more bin per bit for the Kabak engine. Oh, not so important anymore, but at the time it was really important. It required yelling. So fond memories, I have to say. And I'm impressed how Klagenfurt since then has developed the campus, and I think you guys were very smart in using the lake as an amazing attraction to build all these things that are here. And so thanks for having me, and have a good conference.